In the previous lecture, we have seen the comparison of diffraction of electron and X-rays. Actually, in that connection, today we are going to discuss the diffraction of neutrons by crystals. You know that neutrons are microparticles, and according to de-Broglie's hypothesis, wave packet is always associated with any microparticles in motion. So definitely if neutrons are microparticles, we cannot neglect its wave aspect. So quantum mechanically we simply say that neutrons have also wave aspect, and neutrons are associated with wave packets. Okay, and if anything is wave, that must be diffracted. If the wavelength of the wave is just comparable to the dimension of the diffracting aperture, then effectively diffraction takes place. So in case of neutrons too, the crystals are the most suitable diffraction aperture, and so neutrons can also be diffracted from crystals, just in the same way as do the electrons. Okay. Actually, the neutron diffraction by crystals is therefore also in order in connection with the exploration of crystal structure. Okay. As you have seen in the earlier lecture, that we have just discussed the comparison between the diffraction of X-rays by crystal and diffraction of electrons by crystal. On the same line, in today's lecture, our discussion will be just a comparison between the X-ray, electron and neutron diffractions by crystals. Okay, so I am not here going to discuss the complete experimental arrangement, but we will see the important facts uh, which will be just similar or which will be dissimilar in case of the diffraction of X-rays and electrons by crystal and the diffraction of neutrons by crystal. Okay, and when this diffraction experiment is used, for what purpose, we will also see it. Okay, so for this, first of all, we will have to find the wavelength associated with the neutron, because the wavelength of the order of 1 angstrom in case of X-ray or and electron is most suitable for diffraction experiment. So first of all, we will have to calculate what should be the energy of the neutron, which will have a wavelength of 1 angstrom. And for this, we will again use the de Broglie matter wave concept for finding the wavelength of matter wave or material particle. And according to de Broglie's hypothesis, the wavelength of a microparticle lambda is given by h over p, where h is Planck's constant and p is the linear momentum of the particle. And if p is the momentum and E is the energy of the particle, or you can say kinetic energy of the particle, because we always consider potential energy of the particle, in this case 0, because we consider the free particle. Okay, then we know that this E is equal to p square over 2m, where m is mass of the particle. And from this relation, we simply say that momentum p is a square root of 2me. So in case of neutron, p is replaced by a square root of 2mne. Here instead of m, I have written mn, which represents the mass of neutron. Okay, and mass of neutron is equal to what? This is 1.67 times 10 to the power minus 27 kg. Okay. So when you will substitute the numerical value of Planck's constant h, which you know this is, which is 6.63 times 10 to the power minus 34 joule second, and mass of neutron which is this much, and we simplify, then our result will become this: lambda equal to 0.28 over root over E angstrom, where E is measured in electron volt. Remember, in this expression, E is in electron volt, not in joule. So the wavelength associated with a neutron of energy E electron volt is given by 0.28 divided by square root of E angstrom. Okay. Now see from this formula. If we consider that lambda is equal to 1 angstrom, lambda equal to 1 angstrom, then what will be the energy? From this equation 1, you can see easily that energy E will be equal to 0.28 square electron volt. Okay, and 0.28 electron 28 square, this will be almost equal to 0.08 electron volt. So you can say that when we take lambda equal to 1 angstrom, then energy of neutron will be 0.08 electron volt. And you know why I have taken this lambda equal to 1 angstrom? Because you have seen in the earlier lectures that this wavelength is the most suitable wavelength for diffraction work. Okay. And so if your aim is to do the diffraction experiment of neutron by crystals, you should take the neutrons of wavelength wavelength 1 angstrom, and for this you will need neutrons of energy 0.08 electron volt. Actually, the neutrons of energy 0.08 electron volt can be easily obtained from the reactors, and so we obtain such neutrons from reactors and incident those on a crystal, and the neutrons beam get diffracted and we can observe it. Okay. Now in the previous lecture you have seen the relation between the wavelength and energy in case of X-rays and electrons. I am just repeating those results here for your convenience. You have seen that for X-rays, wavelength lambda is equal to 12.4 divided by E angstrom. But here E, mark it, this is not in electron volt, but this is in kilo electron volt. Okay. When you will write it in electron volt, then you have to multiply the numerator by 10 to the power 3. Okay. Then you can write E in electron volt. Okay. And for electrons, you have seen in the previous lecture that lambda is equal to 12 divided by a square root of E, but here E is in electron volt. Okay. And then you get lambda in angstrom. Mark it. You can see that if we take an X-ray of wavelength 1 angstrom, then from this equation you can see that energy of X-ray will be equal to 12.4 kilo electron volt. This is for X-ray. Okay. And from this relation you can see when you will take lambda equal to 1 angstrom, then what will be the energy of the electron? Energy of the electron will be equal to 12 square electron volt, that is 144 electron volt. Okay. So now you can compare the energy of neutron energy of X-ray and energy of electron of same wavelength. Same wavelength, if we take electron, neutron and X-ray of same wavelength 1 angstrom, then energy of neutron you have seen is only 0.08 electron volt. This is for neutron, okay? And for X-ray, this is 12.4 kilo electron volt. It means 12,400 electron volt. And for electron of same wavelength 1 angstrom, the energy is 144 electron volt. So comparing all these three values, we can see that the neutron having wavelength 1 angstrom has much less energy, much smaller energy in comparison to the energy of X-ray and electron. Okay. So I have mentioned it here. You can see that for 1 angstrom, E equal to 12.4 kilo electron volt for X-rays, E equal to 144 electron volt for electrons. Thus, energy of neutrons is much more less than that of X-rays and electrons of the same wavelength. Okay. So for diffraction experiment, neutrons of very small energy of almost equal to 0.08 electron volts are required. Okay. Now, one of the basic difference between the diffraction of electrons and diffraction of neutrons by crystal and X-ray, you can see it here. Actually, in case of electron, you have seen that diffraction of electron takes place by both nuclei of the atom and the extranuclear electrons of the atom, because the extranuclear electrons also repel the incident electron beam, and so that they also play a very important role. But in case of neutrons, the scattering of neutron takes place only by the nuclei, not by the extranuclear electron. Okay? And that's why in this case the scattering factor is nearly independent of the scattering angle and atomic number. Actually, you have seen in the previous lecture, I am just marking it here. You can see that the scattering factor in case of electron diffraction, which was obtained by Mott. This formula I have written in the previous lecture in case of the concept of electron diffraction, that Fe, which represents the scattering factor for electron diffraction. This was given by Mott, and this formula is me square divided by 2h square times z minus fx times lambda square over sine square theta. Okay? And you have seen and discussed in the previous lecture that this scattering factor Fe for electron strongly depends on this theta and z. Z actually represents the total number of electrons or protons in the nucleus. Okay? And theta is the Bragg angle, or you can say the glancing angle. And you have seen in case of electron, with increase in theta, this sine square theta increases, and so that Fe decreases. Okay? And with increase in Z, Fe increases. Z actually represents the total number of protons in the nucleus or total number of electrons in the extranuclear orbit. Okay? But as in this case, you know that neutron has a very smaller size, if we consider that our neutron which have been used in the diffraction experiment have wavelength of 1 angstrom, okay, and the diffraction of neutron takes place by nuclei. It means nucleus acts as a diffraction aperture for the diffraction of neutron. And you know, the diffraction effectively takes place only when the wavelength is of the order of the size of the diffracting aperture. But you know, the size of nucleus is of the order of 10 to the power minus 15 meter. It means 1 fm, or you can say this is 10 to the power minus 5 angstrom. So what we are seeing here? The size of the diffraction aperture is 10 to the power minus 5 angstrom, but the wavelength of this neutron is 1 angstrom. So this nucleus cannot act as an effective diffraction aperture for such a neutron. So in this condition, actually our neutron does not act like a wave. The particle behavior of neutron in this case actually dominates, okay, and that's why we simply say that in this case the particle behavior will dominating. So I have written it here, you can see neutrons are scattered only by the nuclei of atoms of the crystals, and the scattering factor is nearly independent of the scattering angle and atomic number. It means in case of neutron, this scattering factor does not depend on this z and this theta, okay, does not depend. This is because the wavelength of order 1 angstrom associated with neutrons is much larger than the nuclear size, which is of the order of 1 fm, and so their particle character dominates, okay. So even in this case, as z does not play any role here, so in fact in case of neutron, even the lighter element means the elements for which z is small, even those can diffract the neutron effectively, okay. And for example, hydrogen and carbon produce relatively strong neutron scattering, okay, although these hydrogen and carbon will be not very effective in the diffraction of electron, because in that case for larger value of Fe we need larger value of Z, but in this case Z does not matter. So even the lighter elements like hydrogen and carbon produce effective diffraction of neutron beams, okay. And that's why to locate the position of hydrogen and carbon, neutron diffraction is used, particularly in organic compounds in which hydrogen and carbon are definitely present. And if your aim is to analyze an organic compound and locate the position of hydrogen and carbon, then the neutron diffraction experiment will be effective. That will be the actually the successful tool, not the electron diffraction or X-ray diffraction, okay. So this is one of the basic difference between these two between the diffraction of electron and the diffraction of neutron by X-rays. Now, on the other hand, the X-ray scattering cross-section varies directly with electron content. It means when number of electrons in the target is larger, then X-ray diffraction is more intense, because diffraction of X-ray, you know, takes place by electrons, not by nucleus, okay? Because X-rays are scattered primarily by atomic electrons, as I have mentioned it here. So the scattering of X-rays by light elements is very weak, in this case, because the light elements, have a smaller z. Z means total number of electron, and if z is a small, the diffracted beam will be weak. So as you see that even lighter elements is effective in more intense diffraction of neutron beams. On the other hand, the lighter elements particularly either do not diffract, or if it diffract the X-rays, the diffracted beam will have very less intensity. Or you can say that the X-ray diffraction does not take place effectively by lighter elements because it has a smaller electron content. Okay, and this feature of the neutron diffraction enables us to reduce the position of H and C, that is hydrogen and carbon atoms, in number of organic crystals, as I have told you earlier. Okay. Actually, this neutron diffraction is a very strong tool to study the magnetic properties of solids, particularly when you will study in your advanced course of condensed matter physics, particularly the nanomaterials. This neutron diffraction, you will see, is a very strong tool to analyze the nanomaterials, particularly to study the magnetic properties of the nanomaterials. Okay, so I have mentioned it here. You can see a particularly major role of neutron diffraction has been in investigating the magnetic structure of solids. Okay, and for this I have shown here a particular example. You can see this in this graph. I have shown the how the number of neutrons scattered per minute, which is called intensity of the diffracted beam, varies with the scattering angle. Actually, this depends on temperature, which is called Néel temperature. So if the temperature is below the Néel temperature, let us say 80 Kelvin, about this Néel temperature we will study when we will study the band theory of solids. Okay, then you can see that with how this intensity varies with the scattering angle. We see that for a smaller scattering angle, there are two very high peaks, and then the intensity decreases, and again for larger angle of scattering, the intensity is large. Okay, but above Néel temperature, we do not get two high peaks, high peaks for a smaller scattering angle, and again for the large value of a scattering angle, the peaks are very high. So this is just an experimental observation. This graph has been directly drawn here from the experimental result. Okay, so I think you have clearly understand what is the basic difference, or how we can compare the diffraction of electron by crystal, diffraction of X-ray by crystal, and diffraction of neutrons by crystal. Actually, all these have in fact their utilities. They are used in different purposes. Particularly, as you have seen, that if your aim is to discuss or to analyze the magnetic properties of solid, then neutron diffraction will be more suitable. If your aim is to locate the position of lighter elements like carbon and hydrogen, particularly in organic crystals, then this neutron scattering will be more suitable. Okay, so these are the three types of these are three different scattering by crystals. And as I have told you earlier, that this comparison between neutron diffraction, electron diffraction, and X-ray diffraction, this concept, questions on this concept are not generally asked in university examination, but in competitive examination like civil services, when your optional paper is physics, you can see the previous year question. Such type of questions are generally asked. So these lectures will be very helpful for the students preparing for the civil services examination, taking physics as an optional paper. Okay, thank you very much.